Hello everyone, my name is Hongsheng. I'm very glad to have this opportunity to share our work in HV SNP conference. The paper title is LACMUS, Latent Concept Masking for General Robustness Enhancement of DNNs. The authors are Shuo Wang from Shanghai Jiaotong University, Hongsheng from CSIO, Jia Mingcang from University of New South Wales, Benjamin Zihao Zhao from Macquarie University, and Minghui Xue from CSIO. I would like to start this presentation by introducing the background of machine learning. In machine learning, we have training data, and this data can be images, text, audio, and video. Once we have collected this training data, we can put them into a learning algorithm to train a machine learning model. And once the model is trained, it can be deployed in many applications. And these applications can include like chatbot, like image generator, and video generator. But although machine learning and especially deep learning, they have achieved so advanced results, one fundamental problem is the robustness remains an open question. Robustness is important to deep neural networks because in many practical applications, we need to ensure that the model is robustness to different conditions and to different adversarial attacks. However, even in traditional classification tasks, the deep neural networks are suspicious to different kind of adversarial attacks. And now I want to introduce three typical scenarios that the model will cause misclassification. The first one is adversarial robustness. So adversarial robustness means the model can make correct predictions on the original benign samples. But if we add some pixel level perturbations, that is very difficult to notice by human. But the model will make incorrect prediction results and cause misclassifications. The second one is semantic robustness. The semantic robustness means the model can make correct predictions on benign samples. But if we change the semantic condition, for example, like we put the face under different light conditions, the model cannot recognize these samples anymore, and this causes misclassification. The third one is distribution robustness. So some samples, if they are out of distribution, then the model is very difficult to recognize them. And this also causes misclassifications. And so how to enhance the robustness of DNNs? So adversarial training is a popular defense method to enhance the robustness of deep neural networks. So what is adversarial training? So in traditional training, we have benign samples. We just use the benign samples to train the model. And once the model trained, the robustness is not guaranteed. Intuition here is because the model has never seen like adversarial examples. So the robustness of the model is very low. And this is traditional training. So adversarial training is when we train the model, we not only feed the benign samples to the model, we also feed adversarial samples to the model. Because during training, the model now has seen the adversarial samples, so the robustness of the model is enhanced. And this is the process of adversarial training. However, there are several limitations of existing adversarial training method, and we identify 4 research gaps. The first research gap is the current adversarial training, the effectiveness is attack specific. So this means if the adversarial example is generated by attack A, then the trained model can mitigate attack A. But for attack B, the effectiveness is a question. The second research gap is variation specific. For example, if the adversarial example is generated by pixel perturbation-based attack, then the model can mitigate pixel-based attack. But for semantic attacks, the effectiveness is a question. The third gap is robustness and the utility trade-off. Because we have put adversarial examples into the training of the model, so the result is the robustness of the model is improved, but it will affect the normal utility of the model. The last gap we identify is the adversarial example has low-level abstraction, and the feasibility of the adversarial example can be a question. So the first low-level abstraction means it's very difficult to understand what the noise means. And the feasibility means in some applications, we only have limited access to the training data. So we can't have plenty of adversarial examples. And this makes the effectiveness of adversarial training based on large amount of adversarial examples a question. So we offer our solution, latent concept masking for robustness enhancement. That is LACMUS, to improve the existing adversarial training. So in LACMUS, at the beginning, we have a sample X with its label Y0. And we put the sample into the encoder. So the function of the encoder is to map the high dimensional X into the low dimensional representation. And here, each V is a D-dimensional vector. The core idea of LACMUS is we have a pre-trained code book. And in the code book, each C is a concept, and each concept captures the structural attribute of the sample. And each concept is a D-dimensional vector, because the dimension of the concept and the dimension of V is the same. So we can use vector quantization methods to transfer the representation by V to the representation by concept. So once we have the concept metric, then we can use concept masking mechanism to mask one of the concepts in the metric. For example, we can mask the concept of C9 and change the concept of C9 to C0. And once we have finished this step, we can map this concept metric back to the vector metric. And the vector metric is then put into a decoder. And the function of the decoder is to reconstruct the sample X prime, which has the same dimension as the sample X. And we put the sample X prime to the model fx. And we want to ensure that the reconstructed sample X prime, the label predicted by the model is not equal to the original label Y0. If we can ensure that, then together the sample X prime and the label Y0, we construct a new type of adversarial example called conceptual adversarial example. Now we have conceptual adversarial example. Now we can combine the conceptual adversarial example with adversarial training to enhance the robustness of the model. And the high-level intuition is we want to force in the model to make predictions based on essential conceptual elements rather than non-common conceptual features. For the technical details, please check our paper. Now let me introduce the experimental results of the LACMUS. So in the experiment setting, we only utilize less than 1% of the original training sample in both adversarial training and evaluation phase for all scenarios. So the first experiment investigated the utility and the robustness of the model. The research question we asked is how the model utility change when using conceptual adversarial example for adversarial training. And the table 1 here shows the performance of the original model after adversarial training with conceptual adversarial example on clean test and adversarial test image measured by accuracy. And as we can see from this table, the takeaways here is LACMUS maintains or even improves a model's accuracy on clean data and highly improves the robustness against the conceptual adversarial example after adversarial training. The second experiment we want to show is how the model performance against adversarial and semantic attacks. And the question here is how the model's robustness generalized to novel adversarial and semantic attacks. And we provide table 2, the accuracy of models after the adversarial training with conceptual adversarial example against various adversarial and semantic attacks. For example, adversarial attacks of FGSM, PGD, pixel attack, and the semantic attacks of spatial attack and square attack. And this table only shows the results of MNIST dataset. And for the other dataset, we provided in the paper. And the takeaways here is using LACMUS alone enhances a model's resilience against a broader spectrum of CAE, pixel adversarial, and semantic adversarial attacks. The third experiment investigates the model performance against the data distribution drift. We asked the question, how the model's robustness to data distribution drift after LACMUS adversarial training framework. And we provide table 3, the accuracy of the model after adversarial training with conceptual adversarial example against data distribution drift. And we test 2 distribution drift. One is in distribution hard samples, which means the samples is in the data distribution, but they are very difficult to recognize. The other is out of distribution corrupted samples. And the takeaways here is LACMUS has a stronger ability in handling hard and corrupted samples compared to standard adversarial training method. Now we come to the conclusions and the future work of this paper. Conclusions of the paper is LACMUS offers an attack agnostic, model agnostic, robustness enhancement solution with limited number of training samples. The limitation of this paper is more advanced concept replacing strategy should be proposed. In our current concept replacing strategy, although we have some statistical methods for how to select a concept and which position of the concept should be changed, but an automated and adaptive selection mechanism can be proposed to better improve the current LACMUS framework. And there are some future directions of this paper. The first paper is, in this paper, we mainly evaluate LACMUS framework on traditional convolutional neural networks. So what's the performance of LACMUS to other architectures like vision transform models? And what's the performance of the LACMUS to other domains like NLP domain? We also want to emphasize that LACMUS is in its early stage, and in the current LACMUS framework, the encoder and the decoder framework we used is VQVAE. But more advanced generative models can also be considered to be integrated to improve the current LACMUS framework. Thank you for your attention of our paper. For any questions, you can reach me through email. Thank you.